All right, so number 14, find the average rate of change of our function on the interval from 0 to 4. All right, so I want you guys to circle average rate of change, and I want you to write the word slope below it. Anytime we see average rate of change, we're finding a slope. To find slope and use our slope formula, we need two ordered pairs. So the interval that they give us over here, those are the x's of the two ordered pairs that we're going to use. So one ordered pair will have a 0 for the x, and the other ordered pair has a 4 for the x. So what we're missing are the y values. I think the easiest way to find that is on your graphing calculator. Go to your y equals, type in your function, 1/2 times 2 to the x power, and then go to your table of values. You can scroll through your table of values and grab the points where x is a 0 and where x is a 4. When you do that, you're going to get a 0.5 with the 0 and then an 8 with the 4. Now that we have two ordered pairs, let's go ahead and find slope. So slope is y2 minus y1, so 8 minus 0.5 over x2 minus x1, 4 minus 0. 8 minus 0.5 is 7.5, 4 minus 0 is 4, and then when we divide those, we get 1.875. So the average rate of change over the interval from 0 to 4 is a 1.875. All right, number 15, what is the solution to the equation log base 3 of 3x plus 9 equals 3? All right, so we're going to solve for x. Here's our x variable. It's locked in here. It's locked down in a logarithm. So we can't access anything in these parentheses as long as we're in log form right here. So what do? We take this out of log form so that we can get to that 3x plus 9 and do some solving. So when we take this out of log form, we need a base raised to an exponent equal to something. So whatever the base is of your log, this is log base 3, that's going to be our base. And remember, logarithms are always equal to the exponent. So we're going to take that 3, we're going to raise it to the power of 3, and it's going to equal whatever we were taking the logarithm of, that 3x plus 9. Now that we're in exponent form, this equation is not that bad to solve for. Let's go ahead and simplify. 3 to the third power is 27 equals 3x plus 9, and we can solve for x in 2 steps. We'll subtract 9 from both sides. 27 minus 9 is 18 equal to 3x, and then when we divide both sides by 3, we get x equals 6. All right, number 16. Use the properties of logarithms to write the following expression as a single logarithm. Okay, so this is expanded. We're going to put this back together. First thing we look for are exponents. If you remember, exponents are found right in front of your logarithm. So this 6 is an exponent, and that 4 is an exponent. So we're going to start by putting those back. What that's going to look like is this 6 is going to go back to be the exponent there. So we're going to have log of b to the 6th power minus log of c minus, and then this 4 is going to go back to the exponent, log of d to the 4th. All right, so from here, we are going to go work left to right. What we notice is we have this subtraction right here. If you are expanding with subtraction, you can put this back together with division. So this is going to be log of, and then we're going to put this b to the 6 divided by the c. B to the 6 divided by c. I don't know why we have b's and 6's all in the same expression, because when I write them, they look the same. I'm going to carry down this minus log of d to the 4th. All right, so as we continue putting this back together, now we have this logarithm and we're subtracting this logarithm. So again, when your logarithms are separated with subtraction, we put them back together with division. So I'm going to carry this over here. We're going to have log of this first fraction, b to the 6 over c, divided by the second logarithm, which is d to the 4th. Okay, so great. We put it back together, but this is sloppy. We don't like this. So let's just think about how we can simplify that fraction, and then we'll have a nice final answer. So that fraction, we have a fraction b to the 6 over c, and we're dividing it by d to the 4th. So instead of dividing by d to the 4th, when you divide fractions, you can multiply by the reciprocal. The reciprocal of d to the 4th is 1 over d to the 4th. And so we can see that this will simplify to b to the 6 over c d to the 4th. I just multiplied straight across. So this fraction right here simplifies to this fraction over here. So our final answer is log of b to the 6 over c d to the 4th. All right, so number 17, solve the equation 4 to the x power equals 6 for x. All right, well, we had an equation, maybe on the last page, where we talked about, now that you guys are in Algebra 2, you've learned how to solve equations where your variable is an exponent. The one method is to get a common base across your equation. So can we rewrite 4 and 6 with a common base? Well, 4 could be a 2 squared, but I can't raise 2 to a power to get to the 6. So that common base is a great, it's a great approach for solving equations. It just doesn't work every time. So another option is to use logarithms. That's essentially a big reason why we learn about logarithms in Algebra 2 is so that we can solve equations like this. So we're trying to solve for x, which is an exponent. In order to access that exponent, we're going to switch forms. So we are in exponent form. Let's switch this to log form. So when we switch to log form, we're going to say log, and then we need a base. So here we have a base of 4, an exponent of x. So that base of 4 is going to be the base of our log. And then remember, your logs are always equal to the exponent. So this 4 to the x power, that x, that's an exponent, goes over there. And then what are we taking log base 4 of? That 6. So solve the equation for x. We got it. X equals log base 4 of 6. If you guys remember how to find on your calculator where you can change your base of your log function, you could type that in. If you don't remember how to do that, we also learned about a change of base formula. So log base 4 of 6 is the same thing as log of 6 divided by log of 4. And that uses your base 10 button, and that's what that log button on your calculator, that operates in base 10. So then you can just type that into your calculator. And when you do that, we get, I'm going to round to the nearest hundredth, 1.29. Again, you also can type this into your calculator. It's just a matter of, you can't use the log button that you see on your calculator. You have to like dig into one of the menus to find that. All right, number 18, find all solutions to this equation. 2 log of x equals log of 5x minus 6. Okay, so in this, first thing is, you see how we have this 2 multiplied by the log of x? So that's expanded. We can go ahead and put that back to our exponent. So we have log of x squared equals log of 5x minus 6. So we're trying to solve for x, which we have an x here. It's locked down in a logarithm. Here's another x locked down in a logarithm. So we learned another approach to solving equations with logarithms, and that is if we have log with the same base equal to log with the same base, If those logs are equal to each other, then that means what you're taking the logarithms of will also be equal to each other. So that means that x squared will be equal to the 5x minus 6. And now we have an equation to solve where we got out of our logs, and now we can solve for x. If you notice there's an x squared, we do want to get everything to the side of your equation where x squared is positive. And also, we notice there's this other term with an x, so we're going to get everything to one side, so it's set equal to 0. We'll try factoring first. Quadratic formula could be another way to solve this. We'll kind of see how this goes. But because we're going to try factoring as our first way to solve, we do want our x squared positive. So let's subtract the 5x and add the 6. So let's subtract 5x from both sides, add 6 to both sides, and that gives us the equation x squared minus 5x plus 6 equal to 0. Now that we're equal to 0, we can look at this trinomial and think through factoring. When you have just an x squared trinomial, you can jump right to your c value. Do we have factors of 6 that add up to negative 5? Now, because this is a positive 6, let's think through factor pairs. 1 and 6, 2 and 3, those all multiply to positive 6, but they also add up to positive sums, not a negative 5. So if you take your factor pairs, another way to get them to multiply to a positive 6 is if you make both numbers negative. So what about negative 1, negative 6, negative 2, negative 3? And then negative 2, negative 3 is the factor pair that will add up to that negative 5. So this is going to factor into x minus 2 times x minus 3 equal to 0. Now that we have it factored, we use that zero product property and set each factor equal to 0. So x minus 2 equals 0 and x minus 3 equals 0. When you solve those, you get a positive 2 and a positive 3. All right, a couple more problems on this page. Number 19, what is the 8th term of the geometric sequence 3, 6, 12, 24, dot, dot, dot? All right, so to find the 8th term, and just so we get practice doing some good things here, if we wrote an equation for the sequence, a formula for the sequence, then we can easily jump to the 8th term. So just to review, I think the explicit formula would be a nice one to use here. That's an equals a1 times your common ratio raised to the n minus 1 power. So if you know your first term and your common ratio, then you've got your explicit formula you can use to find any term in this sequence. So our first term is that first term here, 3. So an equals 3 times. Now the common ratio is what are we multiplying by to get to the next term, to get to the next term, to the next term? Sometimes you can see it. To go from a 3 to 6, I multiplied by 2. 6 to 12 multiplied by 2. 12 to 24 multiplied by 2. So our common ratio is a 2. If it's not that obvious, you can also set up ratios. You would go to your second term first, 6, and you would divide it by the term before. Then you'd go to the 12 and divide it by the term in front of that, then the 24 and divide it by the term in front of that. Those should all reduce down to the same number. And so you can see that we set up our ratios and we checked that they were common, and that is the common ratio too. All right, now to get the 8th term, that means we want a sub 8. This, when we plug in an 8 for the n, that just means we're going to find the 8th term. So we're going to just go to our equation, our formula, 3 times 2 to the 8 minus 1 power, which is 3 times 2 to the 7th. And when we plug that into our calculator, we get 384 as our 8th term. All right, number 20. Find the amount of money in an account if there was $5,000 invested at 4.5% compounded continuously for 40 years. So I want you guys to circle compounded continuously and underline the word continuously. We have two compounded formulas. One of them is when we're compounding a certain number of times in a year. The other one is when you're compounding continuously. This formula is A equals P times E to the RT power. P is our principal, that's the amount that we are investing or depositing. E is a very common number in higher levels of math. That's a button on your calculator. It's like pi, it's so common it gets its own thing. R is your interest rate as a decimal, and T is your time in years. So we're going to go ahead and plug in our numbers. We said P was the principal. That's what we are depositing. That's that $5,000 times E. Now, E is a number. It's like 2.719, I forget, something like that. Raised to the power of R is your interest rate, but as a decimal. So you have to move your decimal over 2 spots. So it's going to be a 0.045 times T is your number of years. So in this case, 40 years. All right, then we're going to plug that into our calculator. When we type that in, we're going to get back $30,248. And because it's a dollars and cents, we do need to round to 2 decimal places. That's going to round to 24 cents. And that 30,000 looks kind of weird. Let me rewrite. 30,000. There we go. So what's happening is we put in $5,000 and then we just let this money sit there. We went about our lives. Maybe we taught, math for 40 years. Then we retired and we said, okay, how much money is in this account? It was compounding continuously for the past 40 years. And that account got up to $30,000. Well, $30,248.24. The only thing we put in is 5,000. Anything beyond that is interest that we earned on the account. So not bad. Kind of like free money. We just put some money in and let it sit there and collect interest over the years.